Hello everyone, today I'll give a presentation about our work in ISCSLP2022 CSSD challenge. I'm Kylie from Shanghai Voicecomm Information Technology. So here's the outline of my presentation. First, I'll briefly introduce our system. Then I'll give some details about our proposed system. Next, I will introduce the dataset we used. And finally, I will show the experiment and corresponding result. So our system is based on a recently proposed end-to-end vector clustering-based speaker diarization system. This system combines the traditional clustering-based method with the recently proposed end-to-end method. We cite this figure from the original paper. As you can see, this system can be split into two stages. In the first stage, the audio would segment to chunks, and the chunks will send into the system. And then the speaker diarization result and the corresponding speaker embedding vector of each chunk would be the output. And in the second stage, an unsupervised clustering algorithm would be implemented to cluster the speaker embedding vectors and stitching diarization result. In this part, I will give some details of our proposed system, mainly from 5 aspects: the data simulation, conformer, additive margin penalty, spectral clustering, and model average. So we first investigated the data simulation method, mainly based on two observations in our experiment. The first is that as a deep neural network, our system also needs a lot of data for training. And second, compared to the conventional clustering-based method, we only need data with speaker information for training. Our system needs the annotated conventional training data, which is rare in the real world. So to overcome above challenge, we come up with two training data generation strategy. The first is a natural mixture simulation method, and the second is a natural conversational simulation. So the simulated mixture method can be viewed as a sum and a concave method. For a two-speaker case, we will randomly select two speakers with their utterance, and after that, the utterance will be concave with a silence interval in a randomly order. And by this method, man can easily get a lot of data for training. However, compared to the real conversation, this kind of data might lose the naturalness. So to improve the naturalness of the simulated mixture, the transition cases was proposed. The original utterance transition cases include four uh, conditions. There are turn hold, turn switch, interruption, and back channel. In our method, we made some modifications. Um, we simply merged the back channel case into the interruption case. This is because after analyzed the dataset, we found that the back channel case is rare, and we assume if that the later utterance plus the pause is shorter than the previous utterance, then the back channel case would become the interruption case. And the pause of the interruption case, for the pause of the interruption case, we use a uniform distribution um, follow follow the parameter half duration of the previous utterance. And for the turn hold and the turn switch cases, we still use the exponential distribution with a beta we calculated from the dataset. The simulated um, conversation method is similar to the simulated mixture. However, this method directly uses the statistic about distributions of pause and overlaps calculated from the dataset you want to simulate it. So with this method, the data would more similar to the dataset you want to simulate. And we use this method to generate our data for fine-tune. Conformer encoder. The conformer structure was first proposed to use in the ASR task, and compared to the traditional transformer structure, it uses a 2 feed forward macaron-like structure with a convolutional module in between. And with the convolutional and the multi-head self-attention module, it can better dealing with the fine-grained local feature in frequent domain without losing the ability to capture the global feature in time domain. So we replace the transformer encoder with the conformer encoder. The additive margin penalty were the first proposed to solve the phase verification problem. It was designed to reduce the intra-class variance and increase the separability between classes. In the paper, robust end-to-end speaker diarization with conformer and additive margin penalty, the author proposed a modification version for binary cross-entropy loss. The function is like this, where the phi is the label of 0 and 1, psi is the input logis, and gamma is the scale factor. and M is the additive margin value. After analyze the bit loss and the speaker loss in our experiment, we simply modify the function by set the gamma scale factor gamma to 1 in order to balance these two laws. We also tried the label smoothing operation with a speaker loss function. It can be viewed as a regulation technique. For the binary cross entropy loss, we just simplify, replace label 0 with a penalty epsilon and label 1 with 1 minus epsilon. And in the second stage of our system, we found the problem when the audio became longer, the number of chunks would be larger. And in this situation, the original agglommal hierarchy cluster would become worse because it rely on a human-stated stopping threshold. If the threshold value is small, then the estimated speak number would be larger, and if the threshold is too big, then and the difference between the speaker embedding would be hard to tell. We investigated the spectral clustering method and found its effectiveness in dealing with long duration conversational audio. The spectral clustering method does not need any human-setted parameter, and is more robust. Finally, in the original system, the model average was done with a human stated range, for example, from epoch 80 to 90. The selected checkpoint in this range was continuous. Thus might have has a similar parameter distribution. To modify it, we evaluate our model on the magic data RAMC DV set and rank the model according to the CDR. With this result, we choose the top K model to do the model average. Next part is the dataset. We have two parts of dataset. The first is the pre-training. The pre-training training set was made by the simulated mixture method and contain 5,261 hours. And for the fine-tuning training set, we generated by simulated conversation method, and the duration is 2,480 hours. Next, I will show the experimental result. In this table, we show the experimental with the conformer and the result before fine-tune, before and after the fine-tune. As we can see, with the conformer encoder, our system can get get around 1 point improvement in CDR, both on the DV set and test set. And from these two columns, we can see after fine-tuning on the simulated conversational data, an extra 0.7 point improvement would begin. In this table, we show the experiment with the clustering algorithm in the second stage. So we do experiment in two conditions. The first condition is when the speaker number information is given. In another condition, we estimate the speak number. As we can see, in both conditions, the LC, the spectral clustering algorithm outperform the original agglomero hierarchy clustering system. We found both the EM penalty and the label smoothing can accelerate the convergence of training in our experiment. However, compared to original loss function, where the EM penalty does not decrease the result, applying them simultaneously might lead to a decline. We didn't do many experimental in this aspect, so more ablation studies should be done in the future. Thank you. That's all.